Hello, this is Mr. Henry, and welcome to Lesson 1.7. The essential question says, how do I represent functions as graphs? And that's what we're doing today. We're going to be taking those functions we looked at in the last lesson and putting them on an XY table and graphing them. In the Get the Goofs down here, we have three possible functions, and it asks us if these are actual functions. Are the following functions? So let's check here. Remember, the rule for a function is every input has one output. If you're hitting the Coke button on the machine, you expect Coke to come out every single time. You don't expect Coke one time and Sprite another. So each input has one. 3 to 9, 6 to 8, 8 to 0. Yes, that is a function. Second one down here, 15 goes to 3, 23 to 9, 8 to 4, or I'm sorry, 18 to 4, and 15 to 7. No. 15 cannot go to 3 and 7, so that is not a function. And the last one here, 1 to 2, 4 to 5, 7 to 2, 9 to nothing. That's okay. Again, each input has one output. Actually, can you... I'm trying to think of an example where 9 wouldn't have an input. I guess technically this would be no. Because 9 does not have an input, and every input must have exactly one output. So I guess this would be no, because 9 does not have an output. But I'm actually thinking of I'm trying to think of my math, and I can't think of an example where an input does not have an output. I don't know. But technically no, because that input does not have an output, I guess. So these words are the old words. We've got function, relationship, domain is the input, range is the output. Nothing new there. It's just refresh of the vocab from the last lesson. Alright, so now let's take our function, and it says graph the function y equals 1/2 x with domain Well, let's do it. So we have the function, I'm going to write it over here, y equals 1/2 x. There we go. With domain of 0, 2, 4, 6, and 8. So what we want to do is we're going to do the same thing we did before, except we're going to, after we plug in our range, our y values, our outputs, we're going to graph it in our graph space. That's all. So y equals 1/2 of, what's half of 0? Well, 0. Anything times 0 is 0. What's 1/2 times 2? What's half of 2? 1. What's half of 4? 2. Half of 6 is 3, and half of 4 is, no, half of 8 is 4. So now look what we have here. We have an x, y pair. The x value, the y value. That is the first point. X value of 0, y value of 0. Remember that these are your x values, these are your y values, positive 1, 2, 3, 4, positive 1, 2, 3, 4, and going this way would be a negative x, going this way would be negative y. So the second point is 2 in x, 1 in y. 4 in x, 2 in y. 6 in x, 3 in y. 8 in x, 4 in y. That is our function. We are not going to draw a line through them because this function is literally at just those 5 points. It's not at every point in between. We're looking at it just at those 5 inputs. Eventually we'll be looking at functions where we will draw a line because it will be every point on the line as well. But for now, it's just those 5 points. Letter B. We want to graph the function y equals x minus 2, and it gives us this domain. So the domain is -3, -1, 1, 4, and 6. So we're going to plug in the x values to get our y values. So -3, so if I plug in a -3, -3 minus 2, I know this is a little harder, we haven't done integers yet, but -3 minus 2 would give us a -5. Because if you're at negative 3 and you get 2 smaller, you'd be at negative 5. If you plug in a negative 1, if you're at negative 1 and you get 2 smaller, you're at negative 3. If you're at positive 1 and you subtract 2, so 1, 0, negative 1, now we're in easy land. 4 minus 2 is 2. 6 minus 2 is 4. So again, we got positive x, negative x. Positive y, negative y. So we're going for at negative 3, negative 5. So negative 3 in x, negative 5 in y. I think it's this one. Yeah. And then negative 1, negative 3, positive 1 in x, negative 1 in y, positive 4 in x, 1, 2, 3, 4, positive 2, and 6, and 2, 3, 4. And there we go. That is our function that's represented by the y equals x minus 2 at those points. I would like you to try this problem, please. This says graph the function y equals 2x plus 1 with the domain of negative 2, negative 1, 0, 1, and 2. Go ahead, pause the video, do this right now, and we'll get back together in just a second. Okay, so these are for your x values. My x's always look like that. X values, y values. The x values we're using negative 2, negative 1, 0, 1, and 2. And we're using the function y equals 2x plus 1. So y equals 2 times plus 1. All right, so if we plug in a negative 2, the first value, negative 2 times 2 is negative 4. And negative 4 plus 1 would be a negative 3. If you plugged in a negative 1, 2 times negative 1 is negative 2, plus 1 is negative 1. Now we're in easy land. 2 times 0 is 0. 0 plus 1 is 1. 2 times 1 is 2. And 2 plus 1 is 3. And 2 times 2 is 4. And 4 plus 1 is 5. Alright, so now we're going to graph this. So we need our x value at negative 2, our y value at negative 3. It's negative 1, negative 2 in the x, negative 1, negative 2, negative 3 in the y. Negative 1, negative 1, 0, 1. That's 1 in y, 2, 3, 4, 5, 1, 2 in x, and y. Alright, so we got 0, 1 done. 1, 3. So you go over to 1 in x, 3 in y, 2 in x, 5 in y. And that's our function. Okay, so that's been pretty easy so far. They give us a function, they give us the domain, we plug those values into the function for the x, do the math, get our answer for y, plot the points. That's what we've done so far. Now, in example 2, it's giving us the complete table, and it wants us to graph the function. So it says here, the table below shows the average grade on a math test for the first 5 chapters of the book. We've got 89, 76, 66, 73, 84, and we want to graph this function. Okay, so it really doesn't matter too much how you do it. I mean, you need your x values and your y values. You've got your, this would be the x and the y. The grade you get depends on the chapter, because, for example, chapter 3 is really hard, and actually chapter 3 of this book is really hard. So chapter 1 is easy, get a good grade. Chapter 3 is hard, so the grade you get depends on the chapter. The chapter does not depend on the grade. Okay, so this is for your grade. I'm sorry, this is for your chapter, and this is for your grade. So chapter 1, chapter 2, chapter 3, chapter 4, chapter 5. Now, as far as grades, we've got to get our grades up to about, well, the highest one is an 89. Now, I can go 10, 20, 30, 40, 50, 60. That doesn't even fit. 20, 40, 60, 80, 100. But if I did that, don't copy this. I'm going to show what happens if you do that. 20, 40, 60, 80, 100. All your grades, or almost all your grades, are going to be between here and here. That's going to look pretty sloppy. I mean, you're not going to be able to tell big differences between these if you go like that. So if we could zoom in on just that area, it'd be good. So maybe if we went from, say, like 65, because the lowest one is 66. Let me change color again, back to blue. So like 65, 70, 75, 80, 85, 90. That would work. 65, 70, 75, 80, 85, 90. And the way we're going to do this is we're going to do this thing. It's called a break in the scale. So we're going to make this little symbol that looks like this. Almost like the heartbeat monitor thing. It's showing that we're breaking the scale. It's almost like you take this long line and you put your hand on top here and you put your hand on bottom here and you push it together. Well, the paper is going to have to bend in the middle someplace. That's what we're doing. We're just cramming this scale down. Now we can graph, and we know that nothing is important is happening down below here from 0 to 65. All the important stuff is up here. So chapter 1, you get an 89. Chapter 2, you get a 76, which I know that looks like a 6. It's actually a 5. It's ugly. Chapter 3, you get a 66. That's the hard chapter, or one of the hard chapters. Chapter 4, you now get a 73. 73, it's in there someplace. Chapter 5 is an 84. So that's one way you can do this graphing. We have this break in the scale that's used to basically say, I don't really need to look at anything from 0 to 65 because there's nothing happening down there. So we put this break that allows us to have a better scale to show more differences. Example 2. The table below shows the profit in thousands of dollars. So I'm guessing P stands for profit. P-R-O-F-I-T. For a small toy store each year from 2000 to 2004 as a function of time in years since 2000. So this is years since 2000. So 0 years would be 2000. 1 year since then would be 2001, 2002, 2003, 2004. Got it. Graph the function. All right, so time is almost always independent. So you got your T, you got your P. Scale, well, based off the space they give us, 1, 2, 3, 4 is going to work best. Now, the scale on the other side, we've got to think about a little bit. What's the biggest and what's the smallest? So what do I have to go between? The smallest one I see is 19.5. The biggest one I'm seeing is 22.7. So this would be another case it would not be good to count by like tens or fives, like 5, 10, 15, 20, because everything's going to be between like here and here. So if we can find maybe a better scale, it would help us out. So from 19.5 to 22, so let's see, like 19, 20, 21, 22, 23, that would work. So we break our scale. We got a broken arm in there. 19, 20, 21, 22, 23. Now everything's going to be between 19.5 and 22.7. So that's a much bigger space. We can see the differences a lot better. So, and we also have in the year 0. Don't forget about him. So in the year 0, 19.5. 1. 20.3. Well, that's less than half, so in there someplace. 22.7. Well, there's 22. There's 22.5. So 22.7's up there someplace. 3. 21.1. All right, so 21.1 is just over 21, so just above the line. And the last one, 21.8, is like there. Now, that is a function, because each input only had one output. It does not look like a straight line, and that's okay. Not every function will. Sometimes you're going to get functions that are really like scattered about, and it's okay. As long as each input has one output, it's a function. All right, so 2 problems to try out of the textbook. Number 1 says graph the function, and unfortunately I didn't give any graph space on your paper. My bad. You can just make a little XY table like or a little XY grid, hopefully neater than mine, like that. Maybe on the bottom, or on a separate sheet of scrap paper. You can do that. Is fine. And then number 2 says in example 2, suppose use a scale x-axis from 0 to 520 in units of 1. Describe the appearance of the graph. So go ahead, do those 2 problems, pause the video. When you're ready to continue, hit play, and we'll go through them together. All right, so number 1. First thing we need our little XY table. So XY, we need the values 1, 2, 3, 4, and 5. That's a little sloppy. That's what I get for going quick. 2, 3, 4, 5. Slow and steady wins the race. All right. Now we need to plug in those values for x and do the math and get the y. So if I take 1 and plug it in, 2 times 1 is 2, minus 1 is 1. Plug in 2. 2 times 2 is 4. 4 minus 1 is 3. Plug in a 3. 2 times 3 is 6. 6 minus 1 is 5. Plug in the 4. 2 times 4 is 8. Minus 1 is 7. Plug in a 5. 2 times 5 is 10. Minus 1 is 9. All right. So now we need to graph this. So we need to graph the point x is 1, y is 1. 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. X is 2, y is 3. X is 3, y is 5. 1, 2, 3, 4, 5. X is 4. Y is 7. 1, 2, 3, 4, 5, 6, 7. Above the 4. And 5 and 9 would be like that. So I did the best with what I could. If you have graph paper to use, awesome. If not, that's what we got to do. Now example 2 says, suppose you use the scale from 0 to 520 by units of 1 without the break in the scale, without that guy here. How would that change the graph? Well, if you would imagine doing that, I'm going to erase this here. If you'd imagine doing that, what you would get is you'd get a graph that looks like this. So you got your 0, 2, 4, 6. Now imagine you go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the whole way up to 520, counting by ones. That would mean the graph is basically going to look like this. If you're plotting these points here, you're going to see you're not going to be able to see the difference in them because you have to account for all this other space. So the space between 510 and 518 would be like really, really tiny because you have 520 other numbers down here that are taking up all this extra space. So you basically have something that looks almost like a straight line, but the changes would be very small. That would be the difference. Example 3. Write the rule for the function, identify the domain and range. Okay, so now they're giving us the graph, and they want us to go backwards and find the domain, the range, and write the rule for the function. Now, I helped us out here a little bit to start with letter A by giving us the x values, which, by the way, is the domain. So negative 2, negative 1, 0, 1, 2, 3. So let's find the range. So my x value of negative 2 has a y value of negative 1. It went down 1. The x value of negative 1 has a y value of 0. X value of 0, y value of 1. X value of 1, y value of 2. X value of 2, y value of 3, and 3 and 4. Range, negative 1, 0, 1, 2, 3, 4. Now, what's the rule? What's happening from here to there? Now, if it helps you by starting to look at the positives, do that. I usually do. I usually skip the negatives for a little bit and start positives, and then just make sure my answer works for the negatives as well. So look at the positives. What's happening? It's getting bigger by 1. You're taking the x value, you're adding 1 to it, and that's giving you the y value. Well, that is our rule. That's what we would do to get from the x value to the y value, and that does even work for the negatives. Negative 2 plus 1 is negative 1. So write out your table first, get your domain and range, and then look for the pattern in the table to write the rule. So really nothing new here. Letter B. Write the rule, identify domain and range. Okay, so we have our line, or our points, our points that make something like a line. So let's see. I'm going to start over here and just work my way over. So the x value is negative 1, negative 2, negative 3. So the x value of negative 4 has a y value of 1, 2, 3, 4. Next point. The x value of negative 1, negative 2, negative 3 has a y value of positive 2. X value of negative 2, y value of 0. X value of negative 1, y value of negative 2, x value of 0, y value of negative 1, negative 2, negative 3, negative 4. And I don't know why I have an extra box here. All right, domain. Negative 4, negative 3, negative 2, negative 1, 0. The x values are the domain. It's the inputs. The range is the outputs, the y. 4, 2, 0, negative 2, negative 4. All right. So now we need to find this rule. Well, let's think. What would we multiply this by to get that? Well, if you notice, the signs are changing in almost all of them except for that one. But here, like negative, positive, negative, positive, negative, positive, positive, negative. So my guess is you're multiplying by a negative something. And I'm going to show you a little trick. I'm going to give you a preview of something that's far in the future called slope-intercept form, because I think it'll help you out here. If you imagine this is a line, where is it crossing the y-axis? Right there. That is the B point, negative 4. So we're going to take our x value, multiply it by something, and then subtract 4. Well, we've already established it's a negative. So we're going to take our x value times by a negative something and then minus 4. So let's look here. I'll just pick one. I'll pick this one. Why not? So what would I have to... Negative 3. So if I have y equals a negative something times by negative 3 minus 4, and we want that answer to equal a positive 2. Well, guess and check. What's negative 1 times negative 3? Positive 3. Positive 3 minus 4 is negative 1. Shucks. Okay, what if we used a negative 2? Negative 2 times negative 3 is 6. 6 minus 4 is 2. So the pattern here is we're going to take the x value times by a negative 2 minus 4. It's a hard problem. I don't expect us to get this right away. It's a hard problem without knowing this slope-intercept form stuff, which you don't know about yet. We will be spending a lot of time throughout this school year talking about slope-intercept form. You will not be seeing many problems this difficult. Most of the problems you'll be seeing are more like that first example. The rule is y equals negative 2x minus 4. This next example is also a little hard, similar to the last problem. But give it a shot. See if you can figure out what the rule is, find the domain, the range, all that stuff. If you can find domain and range, awesome. And then we'll work on the rule together if you'd like. But go ahead, pause the video, do it on your own. When you're ready to continue, hit play, and we'll go through together. Okay, so let's find our points here. So the first point here is at 1, 2, 3, 4, 5, negative 6 and 0. 1, 2, 3, negative 4 and 1. Negative 2 and 2. 1, 2, 3, or 0 and 3. So the domain is negative 6, negative 4, negative 2, 0. Range is 0, 1, 2, 3. Okay, now, as far as the pattern, it has to be something, a multiplier divide, because we're getting the signs are changing and stuff here. So you're going to be y equals multiplier divide something x, but then it's going to have to be a plus 3 because you're going from 0 to 3. So you're probably going to have to add 3 to it. So we've got at least that much. We just don't know what this number is yet. Well, pick something. Imagine you pick 1. Start someplace easy, and then we can go a little bit harder. So plug in 1. So what happens if I take 1 times negative 6 and then add 3 to it? Do I get 0? Well, 6 times negative 1 is negative 6, plus 3 is negative 3. Well, I didn't get 0. Okay. So try something else. How about 0? Because we have to get a little bit smaller. So if I plug in 0, 1 times 0 is 0. 0 plus 3 is 3. Well, that didn't work either, because the first time when we plugged in 1, we got a negative 3. Now we got a positive 3. We want something halfway between there. So halfway between 1 and 0 would be 1 half. So if we do 1 half of negative 6, what's 1 half times negative 6 is negative 3. Negative 3 plus 3 is 0. That actually worked. Okay. So what happens if we try a number that's not negative 6? What if we use, like, how about this other one? This negative 2. And we want it to, it should, if we're doing it right, if we plug in negative 2, we should get a positive 2. Remember that. So half of negative 2 is negative 1. And negative 1 plus 3 is positive 2. Okay. So that's the rule that seems to work for us. We were able to find this plus 3 thing. Also, you can look at the chart. Remember where I said where it crosses the y-intercept? The y-axis here? It crossed at a positive 3, so we put plus 3. And then you can guess at what this is using a guess and check method. Y equals 1 half x plus 3. Again, this rule was quite hard. You will not find many of them this hard in the future. But for now, I would like you to, it says, write a rule for the function represented by the graph, identify the domain and range. So basically we did in the last 2 problems. And then here, based on the graph below, is 1.4 a reasonable prediction for the chain sales in 2006? go ahead and do these 3 problems and pause the video, do them. We'll get back together in just a second. Okay, so you should be done. So let's see here. We're going to write a rule for this function. Now, I don't have an answer key, so I'm just kind of winging this on my own so you can hear my thought processes. First off, I'm going to find my x, y's so I can make a little table so I can find the rules. So x is 0, y is 5. X is 1, y is 4, x is 2, y is 3, x is 3, y is 2, and then 4 and 1. So as the x's are going up, the y's are going down. Okay? Now, remember that one little trick I said about where these dots, where they would cross the y-axis? It looks like they're crossing at 5. If you imagine this as a line, the line is crossing the y-axis at 5. So my rule is going to be something like y equals something x plus 5. Now this something is a multiply by something, and I don't know the multiply by what yet. Now let's plug in. What happens if we plug in 1? Well, we plug in 1, y equals 1 times 0 plus 5. Y equals 1 times 0 is 0. 0 plus 5 is 5. So that worked out for the first point. Awesome. We might be on the right track. Let's try point number 2. If we plug in a 1, we should get a 4. 1 times 1 is 1. 1 plus 5 is 6. That didn't work. We need something smaller because we wanted to get 4 and we got 6. So we need to get a smaller number. So 1 is not the thing we plug in there. What about if we plugged in a 0? Well, it's going to work for the first one. 0 times 0 is 0. 0 plus 5 is 5. Got it. What happens if we plug in the 1? We're plugging in this point. 0 times 1 is 0. 0 plus 5 is 5. We're not at 4 yet, but we're closer. We were at 6. Now we're at 5. So if we get this a little bit smaller, it'll work. What if we plug in smaller than 0 is negative 1? Plug in a 1. Negative 1 times 1 is negative 1. Negative 1 plus 5 is 4. That worked out. Okay, so let's plug in the next point, see if it works. So if you plug in him, plug in a 2. We're trying to get 3. So negative 2 times, 2 times negative 1 is negative 2. Negative 2 plus 5 is negative 3. That worked. And what we'd find out, if we keep plugging in all the numbers, these will all work. 3 times negative 1 is negative 3. Negative 3 plus 5 is negative 2. This is the rule. Now, I'm going to go a little bit farther in this slope-intercept form to help you out, because I can't think of a better way off the top of my head to explain this. So we've seen how to get this number. This is where the dots look like they're crossing the y-axis. This number is based on, it's called the slope of the line, how slanty the line is. This line is going downhill, so it's a negative slope. This line is going uphill, so it's a positive slope. So that tells you the sign of this number, if it's going to be a positive or negative. And the only other thing I can do to help you out is the more steep a line is, the bigger this number will be. If this line is kind of flat, like that other example here, this line's more shallow. It's not straight. I mean, this would be, that's an ugly line. If the line was like this, this line has a slope of 1. This line is more shallow. It's not quite as steep. That's why the line had a slope of 1/2, and it was positive. Let's go back even farther. Line was going down, slope was a negative number. Line was going up, slope was a positive. In this case, it's actually a positive 1, but it's a positive number. Okay? So we're going to use that, and by the way, identify the domain and range. So this is domain. So I guess we should finish up the problem, huh? We found the rule. Let's do domain. I know, my brain's jumping all over the place. So rule, domain, range. Domain is 0, 1, 2, 3, 4. Range is 5, 4, 3, 2, 1. That's number 1. Get it? Got it? Good. I'm erasing it. Got to do that's number 3. Got to do number 4. All right, so first off, we're going to make an XY table. This is number 4 now, so XY. 1, 2, 3, 4, 5. This will be 5, 10, 15, 20, 25. So at 1, 10, 2, 15, 3, 20, 4, 25. Okay, now let's use all of the information we've done so far. So where does it look like this line is going to cross this y-axis? It looks to me, if we keep following it, it's going to cross right there. So our rule is going to be y equals something x, and that's a positive 5. Follow so far? It's crossing, if we imagine this as a line, the line would cross the y-axis at positive 5. So we put a plus 5 out here. Now, we said this is a positive slope, so it's going uphill, which means this number out here is going to be a positive number. So we can already eliminate all the negatives. It's going to be a positive something. Now we just got to figure out positive what? Well, let's use this first one, and we're going to make an educated guess. So if we take 1 times something plus 5, we want it to equal 10. Well, 1 times what? 1 times 5. 5 times 1 is 5, plus 5 is 10. Let's see if that works for the rest of them. If I plug in a 2, 2 times 5 is 10, plus 5 is 15. Good, that worked. Plug in a 3. 3 times 5 is 15, plus 5 is 20. Good. If you plug in 4 times 5 is 20, plus 5 is 25. That is our rule. Y equals 5x plus 5. Domain, range. Domain here are the x values, 1, 2, 3, and 4. Range are the y values, 10, 15, 20, and 25. This is number 4. And make sure you got it, because I'm going to erase this part here to do number 5. 3, 2, 1, gone. All right, number 5. It says, based off the graph below, is 1.4 million, which would be right here, would that be a reasonable prediction for the chain's sales in 2006? Well, let's see. So this is the year 1999, 2000, 2001, 2002, 2003, 2004, 2005, 2006. So we want to know, would the dot be here? Well, look at the pattern. Look at how the dots are going. Would it make sense for the dot to be up here? If we even got like a straight edge, and followed the lines, does that dot match what most of the other dots are doing? My opinion, no. My guess is in 2006, the sales would be around, I don't know, what is that? 1.1 million? No. 0.8. Oh, yeah, that. Yeah, 1.3 million. There you go. 1.3 million. Yeah, because that's 1.4, 1.3, 1.2. Or my scale's completely off. All right, let's think about this again. That went up by 4. Oh, so this would be 1.4. 1.6 would be here. So would the dot be here? Well, that completely changes the answer, because then the answer is yeah. See, it helps to actually look at the scale. So my guess is yes. That would be a reasonable guess, because I was stupid with my scale. That would be 1.4 million on this line, and that's where we think the dot should be. So yes, 1.4 million is a good prediction. I messed up because I was wrong looking at my scale. Each line here, it's counting by 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4, 1.6. I did not look at the scale close enough, and I made a mistake, and I was thinking it was counting by something else, by 0.1. That messed up my scale. When I went back and fixed it, that is 1.4. That dot does follow on the line that we think it should be, so yes, it is a good prediction. All right, so the last thing we have to do here is answer what are the different ways we can represent a function. Go ahead and think about that. All the different ways we've represented functions in this lesson and the last lesson. Write down your answer, pause the video, and then we'll get back together here in just a second. Okay, here's what I came up with. I came up with the ways we've done it so far is we've used an equation, we've used a table, and we've used a graph. And actually, what you'll see here is I have an example of each. This equation, this is what it would look like as a table, and this is what it would look like as a graph. So all three of these are the same function, just in the different ways that we've written functions before. Equation, table, and graph. Homework comes from page 46, numbers 1 through 6, 9 through 11, 13, and 16. This has been lesson 1.7. Thank you for watching.